Alright, time for another DraftScience video presentation. So we have a reasonable enough comment, and I know you've covered Michael Van Biezen in the past, but he has a clear video. Okay, that there's nothing. It's just the same old gobbledygook. A clear video of the difference between kinetic energy and P momentum. No, there's no clear distinctions drawn at all. He just describes the two things and says they are something. Just a rationalization, frankly. But anyway, we'll play that video. We'll play the first one. Well, I'll get to that. From the standpoint of traditional physics, so there's no explanation of why we need the second formula, why the kinetic formula has any meaning at all, why momentum doesn't perfectly explain the transfer of force into objects, and that the objects can just understand, you can just understand the object is carrying a force. That works perfectly fine. Momentum is just weight. I can say that over and over again. Momentum is just telling you your weight. You have no momentum. Let's say I'm in a non-gravitational field just sitting in space. I put a scale under me. I don't weigh anything. No matter where I put the scale, I don't weigh anything. The only reason why we weigh something on Earth is because, guess what? There's a force acting on us. That's why we weigh something. It's because it actually gives us momentum. So momentum can be just measured by any scale. You just put a scale and say, it hit the scale there. It has momentum relative to the scale. Relative to the scale, they have different vectors, period. We don't know whether the scale moved into the object or the object moved into the scale, but we know both of them were involved. We know whether they both contributed half a finger or whether one gave all and the other one gave all. It doesn't matter. We know they had to have this actual quality of moving in opposite directions. Alright, anyway. So he provides the title, which is good, and from the title we can find the video, and so everything's just fine. Where the hell is it? Spaghetti Western? No. There, that looks like it. So we'll go there. So what I'm going to do in the future now, I'm going to work on, is putting a chart together. I'm simply arguing that this is just, some sort of religious argument. Okay, and this is just a philosophy argument it's turned into. And there's really clear sides. I mean, there's the Newton, Descartes, even Galileo side over here. I mean, Galileo was a little bit of a relativist, but he certainly wasn't squaring the velocity. And over on this side you have Leibniz and Huygens, and Young is even involved, the guy with the double slit nonsense. So the same players. It's the relativist against the real universe. The universe is made out of real stuff in real three-dimensional space versus three-dimensional space is an illusion. Nothing really has anything. Everything's being moved by an ether. Everything's a wave. Nonsense. Clearly, it's evolution against smevolution. Okay, it's smart against silly. And I'm going to demonstrate that because the evidence is overwhelming that the kinetic energy formula is a mere contrivance. It's just nonsense. It's just, I could compare it to the Holy Ghost, right? In Christianity. It's just useless crap, okay? But a Christian could sit there and rationalize it. Little bird outside the window. Hi. Snow and everything out there still. Anyway, snow. Anyway, so I mean, so they can rationalize, right? They could go, well, it's not the Holy Ghost. In the original Arabic, it was the Holy Phantom, right? Phantoms are like ghosts. And then they could say, well, the Phantom of the Opera was a lot like an invisible man, right? That's why they called him a phantom, because he was like the invisible man. Well, obviously, invisible men are called invisible men, so it's not really the Holy Ghost, it's the Holy Man. And holy man, that's what they call like the Pope. So he was just like the Pope. The Pope was in between Jesus and God. See, it's just a rationalization. It's just a pile of crap they could just make up to try to make this crap make sense. It makes no sense. It is insane. If they had to really stake their life on it, they wouldn't. Okay, and I'll give you the clearest example of why the kinetic energy formula is absolute nonsense. I mean, I've already given you plenty of examples of how it doesn't work. It's bibble. It's nonsense. But anyway, So I have alluded to this spaceship idea. So you're in your little spaceship, okay, flying through space, and you want to turn because you want to go to Candyland. Yes. All right, and you can't get there unless you turn the ship. But your ship has this thing about it, okay? You from one side of the ship, you can shoot only things that have, let's say you can only shoot things at a certain velocity, okay? And from the other side of the ship, you shoot them from twice that velocity. So so you have little lumps of crap that you can shoot, okay, out the side of the ship. Okay, and that'll make you turn because you're doing the equal and opposite reaction thing. So these go out at 10 miles an hour and these go out at 5 miles an hour, right? So I would say if you want to get to Candyland, you're going to have to definitely shoot more from one side than the other side. Now, because of their kinetic energy formula, okay, they think these have a lot more energy, okay, from coming from this side because they leave at 10 miles an hour. And the ones from over here have a lot less energy because they're only going 5 miles an hour. Now, if you wanted to turn, you'd say I have to shoot more from one side from the other side, but it's not going to work. Let's say you have to go straight. Or let's say, well, it doesn't matter. I'm just saying, understand, so to turn, to have the same amount of pressure on both sides. Let's say we just wanted to do that for the fun of it, to test our engines, and now if the test is going to tell us how we're going to turn to get to whatever fun park. So the rule is 10 and 5. So logically I would say, okay, well, you got to shoot 4 5s. Let's say we shoot the 4 5s out. Okay, so we have 4 5s, 5 miles an hour. Things fly out the side of the ship. Now that's a certain amount of energy you've shot out of the side of the ship. It's going to make you go this way. Now we want to make it go back to the right amount back this way. And so by their theory, okay, they're going to shoot 110. Okay, and they're saying, I'm done. Because the kinetic energy formula is going to say 1 going 10 miles an hour is the same as 4 going 5 miles an hour. Right? When the momentum theory says, no, you have to do 2 of these. Okay, this equals 20, okay, and you have to make this side equal 20. So you have to have 2. All right, so that's what it comes down to, is their theory gets wrong answers. It would say that this has 4 times as much energy as this, okay, and there's no reason for you to believe that, right? No good reason for you to believe you can just shoot 1 out of one side going 10 miles an hour and have equal to 4 going out of the other side at 5 miles an hour. So logically, that isn't going to work. Okay, now I didn't use perfect numbers here, but you get the idea, right? Momentum says one thing, kinetic energy says another. The two aren't compatible. You have to, if you're in the spaceship, you're going to have to invest in one of the theories. Okay, one of the theories is going to be right, one of them is going to be wrong, and that's just a fact. And I'm saying, if any of you idiots had to invest your life in it, like you have to avoid the planet or something, you wouldn't be using your kinetic energy formula. You would be using momentum because it's reliable, it always works, it's the real world, it's just indestructible as a description of what the dynamics of motion are. Momentum describes it completely. All right, you don't need the kinetic energy formula, and you would know it if you're in a spaceship. It's not going to do you any good. It's just going to get you dead. All right. So all of this is just a nonsense conversation. It shouldn't exist in the first place. If in the 1700s they could do these better thought experiments, imagining better environments than the gooey ones on Earth, if they could do more clinical experiments, they would have figured out, oh, okay, we're way off track. Let's just forget this whole Holy Ghost thing. Let's not sit there and bother with it. It doesn't really play a role. It's not important. Let's just call it a mistake that we even thought about it, and let's move on to some kind of rational physics. So anyway, so I will put together a chart. I mean, it's just going to be silly over here, okay, and it's going to be smart over here. And that's all that's really going to come down to. And Newton's going to be on the smart side. Descartes is going to be on the smart side. Voltaire is going to be on the smart side. And the silly side is going to have Leibniz, the lying thief. It's going to have Huygens, okay, the rather silly person. And it's going to have this, whatever the silly woman was. And then it's going to have the you know, the big faker, phony bullshitter of Thomas Young of double slit fame, you know, who did a sloppy ass experiment, drew a picture that was never right from the very beginning, and got everybody to believe that photons were magitons. So anyway, and what's going to be shown is there's tons of experiments over here. I can just list them, millions of experiments, okay, proving momentum is the man. And there's going to be one experiment, maybe another half of experiment over here. Okay, they have 1.5 experiments that give you any reason. I mean, it's not even a good reason, it's just any reason. So they're just taking any possible reason to believe. Okay, see, and the whole thing is really just going to come down to is they think how far you go in distance means you have, that's how much energy you have. So if you go fast, you have a lot of energy. If you go slow, you have less energy. And they don't think mass matters at all. They don't think it's significant. They don't think it means a damn thing. They just think distance. How far did you go? How far did you go? When, you know, obviously we all know that it's easier to push something small. I mean, you can make it go really fast. I could push light things all day long really fast. And you know, obviously that's not my total energy. Obviously it has nothing to do with how much energy it took to move the object. It's how far it goes. No, the amount of energy you have to use is completely dependent on how much mass it has. And that's what all these experiments demonstrate, is that mass is equally important. Okay, velocity is important and mass is important. And the two of them are equally important. And the fact is they equal weight. And they equal energy. And they equal, what else? You know, that's it. They equal force. That's what they equal. When something's moving through space, it's just really saying I'm a blob of force. When a mass is moving through space, it doesn't matter whether it's an atom or an electron or anything, it's basically saying I'm taking the place of a force. So instead of gravity hitting you, I'm going to hit you. Same difference. I have the force. I'm going to interact with you. So it's just, you can call momentum force, you can call momentum weight, you can call momentum energy. It's all of those things. It's the winner. It's the right answer. Okay, I shouldn't have drawn it on the wrong side. And this is just silly. It's a silly history. It's silly. I mean, I could show you the other video, you know, where they compare the bullet and the bowling ball, right? And I gave you the right answer for a bowling ball, right? They had the bowling ball moving 5 meters a second. Obviously, it can only move 0.5, let's say, with the same charge you gave a bullet. So you shoot a bullet and you shoot a bowling ball. The bowling ball goes half of a meter per second. The bullet goes 300. Now, the kinetic energy formula, if I did that, if I actually made it 0.5, right, they had a ratio, right? This is the energy ratio. So I used the same amount of explosive to shoot a bullet, right? So I have a gun barrel. All right, I put a bullet in, or let's say I put a shaft on a bowling ball. So the shaft is inside, so it gets all of the energy. Okay, so there's a shaft in the gun, and the shaft is going to hit the bowling ball. All right, so the bowling ball is going to go 0.5 meters per second. The bullet's going to go 300 meters per second. All right, and they have weights proportional to that, 6 kilograms and whatever, 0.00, whatever the mass is. The point is their kinetic energy formula says the bullet has an energy 456 something like that joules, and the bowling ball, guess how much it has? 7. Okay, 7 joules. So I use the same charge to move the two objects. They say the energy in the bullet is 456. And they say the energy in the bowling ball is 7. 7. Yeah. Same amount of explosive, same energy, same force applied to the two objects. They say one of the objects has this magical, gigantic number, right? An insane number, really. Just insane, crazy. This can't possibly... They have the same exact momentum, but somehow this one has 456 units of energy, and this one only has 7. Now, if you want one of these to bang into your baby, Yeah. So you're going to pick the bowling ball. So let's say I made the bowling ball twice as heavy. So now it doesn't have the same momentum. So now it has much greater momentum. Well, I've only changed this number to 72, right? So I'm still way ahead on energy here with the bullet, right, than the bowling ball. And then I can just keep doing that, right? I can just keep adding more and more gigantic mass, making the bowling ball have more and more momentum, right? And then I said, I gave you a choice. I said, well, we're going to spread the momentum. The bullet's not a little tiny thing anymore. We're going to make the bullet the same size as the bowling ball. We're going to both turn them into flat plates, and we're going to hit your baby with it. Okay? If you go with your kinetic energy formula, your baby is dead. You're going to make the wrong choice, because the thing that really has the energy is going to be this thing. That's the one that's going to win. Okay? The 17-pound bowling ball, okay, is going to have a lot more potential to do damage, all right, than the bullet spread over the same size piece of matter. So anyway, like I said, if there was real stakes here, right, if this was a real duel, okay, you people wouldn't be in the duel, okay, you'd be chickening out. And that's already been demonstrated. I mean, I haven't gotten a single pledge against my claim. I'm going to defend Newton's physics. I'm going to defend all this stuff, and we're basically having a kind of bet. And the bet will basically pay for a really good experiment to prove the case one way or the other. Some kind of really perfect experiment to really just demonstrate that your physics is silly physics. And not one pledge. Not one single person has stood up and said, I'll defend our great American physics. French, really. The silly French people in the 1700s who did their little clay experiments. I'll defend that as good science. Against Newton, against Descartes, against Voltaire. You think they were all rubbish scientists. They were all rubbish thinkers. And you really believe in your Huygens. You believe in your infinite number of waves being created. You believe in infinities. You believe that space isn't 3 dimensions of real space, and that things are in real distances from each other, and they have to move through that distance to actually hit each other. You think that's all an illusion of some kind. Anyway, I digress. But I just... So, yes, but when you put all the evidence together, there's no way you can survive it. When I put all the experiments and show you each one of the experiments and say, how can you explain this nonsense? And they just keep trying to hide behind, oh, it's a vector quantity. It's in different things. It's a scalar. It's just all babble. And you can see the babble. It's just a bunch of Holy Ghost or Holy Phantom bullshit. They're just contriving silly excuses and using semantics to hide the truth. And I can't believe all you people are this dishonest. I mean, this was a wake-up call that smart people... I've always had some suspicion that smart people really are the enemy. That they are just so nihilistic, selfish... they're terrible. They have no integrity. They're the worst thieves. I had some suspicion because I'm just saying, how can things be this dysfunctional for this long? Because smart people have effectively been in control, and they've made a horrible mess out of everything. They never do anything the right way or the honest way or with any integrity. And it's just been a huge disappointment, because I did have some notion that they were like Carl Sagan-y or something, like they really cared about something real, but they only care about their religion. They only care about their bow tie. They only care about wearing their coats and their clothes and their image. Their cap, their Trump cap. They're really just Trumpers. They really do want to just wear it on their head. I'm a silly person. I believe in silly goop. I'm a nerdy retard. Yeah, because you have to be. Like I said, you can't. This is not elusive at all. I mean, all you have to see is those silly numbers. The bullet has what, 196 times more energy. The same explosive moved two objects, and you're going to sit there and tell me one of them has 476 times more energy or something? It's just stupid.
Welcome to Lecture Online. I've been asked by some viewers to explain the concept of momentum in a more fundamental fashion. And I thought, well, let me go look and see what videos I had, and sure enough, I'd never really explained what momentum is down at the very basic.
Well, yeah, you really don't. So you do this a lot, okay? I mean, you were supposed to explain the parallelium or whatever of Mercury, and all you did is say, well, yeah, we just put in this Einstein thing over here, this gamma. You know, never explained how you derive the gamma
Concept. So here's a few videos, starting with this one.
And again, you did draw the two-slit experiment as if the waves are coming out of the centers of the slits, which they're not.
To try and explain what momentum really is. First of all, let's do it graphically. And there's, by the way, two kinds of momentum. We'll get into that.
So again, momentum could have just been called momentum energy, right? Just like they put the word, kinetic, and they put the word energy after it. They could have said momentum energy. They just didn't have the word yet. Okay, but that's really what momentum is describing. It's describing the fact that you're collecting force. When you're in the universe and you're an object, a material object, you're collecting the imbalances in the forces. If there's an imbalance somewhere, you actually collect the imbalance. And now you have it. The wrench flying through space has something. Now, it's either it has less movement or it has more movement, but it has something different than the one on Earth. The one that's not moving relative to the space that we're moving through is obviously moving differently than the one that's moving through space. Now, they both can be moving, but they're obviously moving differently. And they're moving differently because they're being affected by different forces.
In a moment, but typically we think of it as an object that's moving at some velocity. So the momentum, which is written with the letter P, P stands for momentum, is the product of the mass of the object times its velocity. So we may have a very small mass.
So again, the trick is that we can never be sure. Okay, I can shoot the gun and shoot a bullet into somebody, and I can't really say for certain. Well, I mean, there are some logical arguments that eliminate the possibility that it could be anything else, that the bullet actually does have the velocity. But the point is this: all of this matter is moving through space, and at every moment our direction is changing. Because we're on all kinds of moving stuff, hurling, thrilling, spurling. So every minute our momentum is changing direction. But everything here is doing exactly the same thing. Okay, this thing's jerking around just as much as I'm jerking around, going all kinds of different directions. At any one moment, our momentum is in a different direction in the universe. Every millisecond, we're going somewhere else. But we're all doing it collectively. And we're trying to find the thing that's doing something dramatically different. So you could argue that obviously the bullet's doing something dramatically different. Now, the truth is, when you fired the gun, you could have possibly, for parts of the millisecond of the firing, right? The firing happens slower than how many times you change direction, by the way. But anyway, in that process of firing the gun, the bullet, everything is still in that same universe and still being pulled by those same forces. So even though the bullet's leaving in a direction, it's still doing everything the gun was doing. That hasn't changed. So it's still getting jerked around in the same atmosphere, the same world that you're in, blah, blah, blah. But anyway, you have to understand that it's relative and it's absolute. See, this is another part where they make it seem like those two things, you have to choose to live in an absolute universe or a relative universe. No, you can live in a universe that has real velocity. It's all absolute, but you have to look at it relatively. You can only see it relative. But there is a truth, an ultimate truth about exactly how much of the bullet's velocity was my velocity moving into the bullet, or how much of the velocity was all just the bullet moving into me. We could both be going that way. We could both be going in the same direction. The bullet's just going in that direction quicker than I am.
But if it's moving at a very large velocity, it will have a lot of momentum. If the mass is kind of average and the velocity is average, it still has a fair amount of momentum. And even
so again, we can only tell what its real thing is relative to other things. So we can only see which one has which by understanding which things actually are in the universe. Now, you could argue if I'm in a spaceship and I look out the window, I can see the rest of the universe moving by. So unless I believe the whole universe is moving, I would have to argue that, yes, I'm the one who has the changed momentum. But it's really, there's no way to do it outside of a relative comparison. You're just stuck with that. I mean, even a brick wall isn't standing still. It is moving in the universe. It is moving in the 3 dimensions of the real universe all the time. The brick wall is actually moving. But so is everything else in the gravitational field of the Earth, doing exactly the same pattern of movement.
Though the object may be moving very slowly with a very small velocity, if it has a lot of mass, it still has a lot of momentum. Well, that still doesn't explain what momentum is.
I know, you could just say momentum is captured force. It wouldn't be a bad thing to say. If you just said momentum appears to be, you collect force and it's in the object and it keeps moving until another force changes its movement. So you've collected something like Tweety birds or hopping rabbits, you've collected them, and now they're hopping in a direction still. So the force is now inside the object, and the object contains something you call force or energy, or clearly you could just call it weight. It is now differential. It is now something moving different than the rest of the stuff in the environment. So when it hits the spring of the scale, it will measure how much difference there is. So I can jump off the table and I can measure how much momentum I have on a scale. I'll call it weight, but we know it's not my actual weight. We know it's my weight times my velocity. It's my momentum. When I'm standing on the scale, even when I'm not jumping on the scale, I'm sitting here measuring my momentum. You have momentum just sitting on the Earth. The Earth is, in fact, pulling you in, pushing you down more correctly. Let's try to use correct words where we can. I mean, they have screwed up vocabulary, so it's all very dangerous. But let's try to navigate this mushy word minefield with a little bit of discipline, being careful. Understand that they just throw these words out, and you got to be very, very careful what they mean.
But here's a nice definition of it. Momentum is the tendency of an object to keep moving once it's in motion.
So it's not just a tendency. Okay? No. It doesn't, there's no I tend not to. So we know it's the tendency is kind of, that's not the right word to use. I mean, it's an absolute necessity, okay, that it keep moving until something stops it. An equal force has to interact with it to stop it. Or to change it, we need some force to act on it. But it's not a tendency. It's just an absolute fact that it will keep moving until something stops it. And it will do it just like a force. Just like a force, it's indestructible. You can't stop the force. You can only counter the force. Forces can never be destroyed. Forces can never be simply negated. You can't just shoot your ray gun at it, make the force go away. You have to create another force, another hunk of energy in the universe to fight the other piece of energy. Another piece of energy has to change your motion.
So once an object is in motion, the more mass it has, and the faster it's moving, the more momentum it has.
The more force, clearly, you could just say the more force it has, the more energy it has.
And if you look at the second sentence then, to change the momentum of an object will require a force.
Right, so to change the force you've acquired, you have to interact with another force, either in the form of another piece of matter that has momentum, or weight, or you have to interact with another particulate force, you could argue.
Applied for a certain duration.
Right, and this is the other experiment clearly demonstrated in the counter-argument video, is that when you try to stop the bowling ball, it reveals itself. It shows you that you have to apply the force for you have to hit it with the same punch, right? Or you have little hairs that take energy to knock over. The bowling ball will require you to use a lot more hairs to stop than the bullet. In that example, because the bowling ball had more momentum. Now, if we give them the same momentum, it'll take the same number of punches to stop both. So if you just add up how many punches it took, how many pieces of matter you had to throw at it, you'll find out that the same momentum means you need the same stopping force, the same amount of stopping force, the same amount of punches. Again, gravity is punching, but clearly it's the surface, right? It can only take a little punch at one atom, where if you have 10 atoms, it can hit all 10 atoms. So 10 atoms are collecting 10 punches, okay, per second, where one atom can only collect one punch per second. So that's why it takes, that's how gravity works. That's why the heavy object hits the ground with a lot of punches, because it collected a lot of punches, because it has a lot more matter to collect the punches with. I mean, these are decisive arguments, so I'll never get any counter argument to that simple piece of logic right there. That's exactly how gravity works. Things with lots of mass collect lots of energy. Things with a little bit of mass collect a little bit of energy. That's the truth of gravity.
So if you want to change the momentum of an object, let's say an object is moving, it's rolling on wheels, and you want to slow it down, change its momentum, because when you change the velocity or change its momentum, you...
Right, so we know we can't change mass, all right? And what good would it do you anyway? Because if you just threw mass into the air, it's not going to help you any. You have to throw it opposite of your direction, right? See, if the spaceship threw the mass forward, that would mean it would be losing its own velocity. So we're trying to turn the spaceship. That is, we're keeping the velocity in one direction, and we're adding velocity in another direction.
You'll have to apply a force. You will have to push against it, and the longer you push, the slower it will go, and eventually you can stop it. Or, if you want to get something...
So, starting force is the same as stopping force. So the fact is, the stopping force is telling you how much energy produced the motion. It's exactly the same amount. Pushing it to 50 miles an hour will take just as much energy to slow it down to zero again. So it's the same thing. It's a good way of measuring how much energy the thing collected, is merely try to stop it. And the stopping energy will tell you how much energy it actually has. And again, if I convert a bullet into the same surface area that a bowling, in a bowling ball, I take the two ideas and I give them comparable surface area in terms of their impact on you, the pounds per square inch kind of thing, you're going to see that it's the same energy.
Moving, it will require force, because when something is not moving, it has no momentum. And if you want to give momentum to an object, you'll have to push against it for a certain amount of time.
Right, and if it's light, it goes really fast and far. And if it's heavy, it goes really slow and not very far. But it's the same amount of energy.
The harder you push, or the longer you push, the more momentum you will give the object.
Again, same punch. I hit something. 50 pounds. The 50-pound thing moves 2 feet. I hit something. It weighs 500 pounds. It moves 1 inch. Do I say because the light thing moved further, it has more energy? Do I say because the light thing moved faster, my punch had more energy? I mean, it's that stupid. Again, grammar school kids could sort of get this, I think. I think they can really get that the punch only has 50 of something. I can't give something 200 of something with my 50. I can just give it 50. And the heavy thing means the 50 gets spread over all the atoms of the heavy thing. So each atom's going to have a lot less energy. And the light thing has less atoms, 4 times less, or 10 times less in this example. So obviously the punching amount is, if each atom is a pocket that you put the coins in, obviously each atom, okay, is going to, have, there's only $50 to be in the pockets. And if I give the $50 to 10 people, each 10 people is going to have a lot more than if I give the $50 to 50 people, right? Then it's only $1 per person. I give it to 10, they got $5 bills in their pocket. So yes, they're going faster. But it doesn't mean they have more energy. It doesn't mean I gave them more money. I mean, Yeah, a grammar school kid could understand that. And apparently adult, college-educated scientists can't.
Now, I did mention there are two kinds of momentum. One is what we call linear momentum. When a car...
Let's understand, momentum has to be linear, okay, just because it's clearly telling you it's a direction, okay? Now, I mean, I could explode something, and if I explode something, we already know by concept that I'm breaking it into little pieces, and each little piece is going to have momentum in a direction. Now, energy, I could say, well, energy is that kind of description, where you can just say, I gave a bunch of pieces different direction. But we know that the energy of each little piece is in a direction. That you really can't say that energy is ever in a form where it doesn't have a direction, just like momentum. It's just that we're used to using the word energy for things that are in tiny pieces, and we're used to using the word momentum for things that are in whole pieces. But it's really the same thing. They know it. They'll talk about conservation. He has it written down here. Conservation means that they're counting heat as momentum. Well, the heat goes in all directions, but they know the momentum of each particle of heat has a direction. It's just that it's all the directions. Just like light. The photons come out in all directions. But the momentum definitely has a linear character. Each photon is on a linear path.
Is rolling when
as the laser beam proves.
Bicycle, when someone is riding a bicycle, typically these objects, person and a bicycle, a car, a rolling ball, a flying ball, anything like that, it will be, first it has a certain amount of mass, and it will be moving at a certain amount of velocity, typically in a straight path, in a straight line. So we call that linear momentum, and so the momentum is simply the product of the mass times velocity. Now, take a note that...
Look, angular momentum has nothing to do with the concept of momentum in the sense that angular just means we're not going to look at it every millisecond. We're going to look at what it does over time. So we know to have angular momentum, the pieces of matter have to be moving in multiple directions over a very short period of time. You know, it can be a really short period of time. You know, like I can spin a CD really fast. Well, each piece of the CD at any one moment, just like the Earth has a velocity in a straight line. Okay? And it's an applied force that changes where it goes. So at any one minute, its velocity is always in a straight line, and we just keep changing the straight line's vector, the direction of the vector. And that's all angular momentum is. You have to have another force for there to be angular momentum. So like gravity, there has to be some other mechanism that has to be pulling on the atoms, or pushing on the atoms, tugging on the atoms, changing the field that the atoms are in.
Momentum is actually a vector quantity, which means it has magnitude and direction, and that is because velocity is a vector quantity. So we multiply the mass times velocity.
So again, and that would hold for kinetic energy also. So again, it's just bibble babble.
Mass being a scalar, velocity being a...
So again, they try to make this distinction, and it only has to do with the fact that they didn't do the conversion. So if you don't convert something into actual units of energy, like watts, so I could light a match and I could just say its heat index is 56 or something, and I don't put it into some quantity that you know you can convert into watts, then it looks like it's not a quantity, because it's like particles of heat per second over distance or some other, you know, you just make up some crap and you say, okay, I'm not going to convert it into actual watts, even though I can. I'm just going to pretend it's not a real quantity, and that way I can say something's a scalar. You know, no, everything can be the same thing. Okay, you can make a scalar into a vector. You can make a vector into a scalar. You can change them. There's no rules that say you can't just change it. You can just convert it into watts.
Vector, that means momentum is going to be a vector as well. There's a second type of momentum called angular momentum. We can also think of it as rotational momentum. An object that is rotating has momentum. The larger the object, the more mass. The faster it's moving, the more momentum it has. the more angular momentum it has, and we use the letter L to indicate angular momentum.
So again, it's not really what it has now, because this momentum is the momentum of its atomic parts. So it really isn't momentum it has. It's not going somewhere. It's not doing any of that. You have to interact with the little bits that are spinning, and the little bits that are spinning are all going to hit you a little bit different depending on how you interact with their motion. Okay, but it's just really just saying, look, we can't see the universe at a trillion seconds, at the frame rate necessary to see what's really happening. Just as we can't see ourselves, every bazillionth of a second changing direction in three-dimensional space. But we actually are changing direction all the time.
Well, angular momentum is the product of the moment of inertia times the angular velocity. Notice the similarity. Instead of using mass, we use moment of inertia, which has something to do with how easy it is for an object to be.
Okay, so let's just understand that. It has nothing to do with anything. There's no such thing as inertia. It just takes time for energy to get inside of matter. That's all. Matter says you have to pour the water into me. That's it. There's no resistance. Nothing has a resistance to being pushed. Okay, there's no such thing as resistance. It just says I can't have the water in me until you pour the water in me. And it takes time to pour the water in. It takes time to get the force into all the pockets. Just like if I had the $50 and I'm going to put it in 10 pockets, it takes time to shove the money in the pockets. The people don't have the $5 till I actually put it in their pocket. That's all it means, okay? It doesn't mean anything. And the only reason why angular momentum means something in that circumstance is obvious that this is happening so quickly, this exchange of the energy into different pockets to create all this different motion. Okay, but it's just a fact that it did happen. It just happens really fast.
Rotating, and omega, of course, is the angular velocity, the way we express how fast something is rotating. The faster it's rotating, the larger the angular velocity. Notice omega is v over r. If we take a point at the edge of the disk and we measure the radius of the disk, then omega will simply be equal to the velocity divided by the radius, which is called the angular velocity. The moment of inertia of a solid disk is half the mass of the disk times the radius.
Right, it's always half. Okay, that's gravity. So the angular momentum has the same half in it. Okay, it's basically telling you the same rule sort of applies. That, in the first second of your motion in gravity, you only go half the distance of your actual velocity. Your velocity is 22 miles an hour. You only go 10 miles. You don't go the 22. So in the first second, you're somehow not moving 22 miles an hour. You're moving something less than 22 miles an hour as an average. But clearly, since your velocity is increasing through the whole process, your net velocity is meaningless, because the only velocity that's really going to matter is your end velocity, which is the 22 miles an hour. So even though you travel the short distance, you gain the full measure of velocity.
Radius squared. So if you need to know more about the moment of inertia, there's lots of videos in the channel to show you what that is as well. But at least now you have an idea that an object can have momentum, angular momentum if it's rotating, and it can have linear momentum if it's moving in a straight line.
It's just about moving, and the fact that you're changing the direction of the movement a lot when something's spinning. Okay, you're obviously changing it from this way to that way, right? You're changing it in all kinds of very dramatic ways. Each atom, I could just put a little spot on the spinning disk and whoa, each atom is really doing a lot of changing in its direction.
Finally, the nice thing about the concept of momentum in physics is that momentum is always conserved.
So they use this word conserved, and they don't mean it in the transfer sense. Okay, so obviously you would say the momentum isn't conserved if I throw the bowling ball at the wall and it half bounces, it bounces off a little bit, some of the chips fly off of the wall, blah blah blah. You wouldn't say I conserve the momentum in the sense that you didn't transfer it. right? So if I crash two bowling balls into each other made out of glass, and the glass shatters and pieces fly all over the place, I wouldn't say I transferred the momentum. I certainly didn't conserve it in the transfer. Yes, but I shot off pieces, and the pieces have all the momentum, just like the spaceship. The light pieces will go fast, the big pieces will go slow, but they all have this, they're all carrying some force. And I didn't kill any of the force. All of the force is conserved. So conserving all of the force and transferring all of the force are two different things, and they talk about them using this conservation word, which is really destructive to understanding. Both sides, the silly side and the smart side, believe in conservation of energy. So, well, see, I can't say that because they don't think you have to conserve kinetic energy, that you can lose it to something. It can disappear from the universe. But they won't say it disappeared from the universe. They'll say it was in little pieces of glass that flew off, or it was in heat or something else. That's the conserved momentum. You can't conserve the momentum as heat and then claim that you conserve the momentum. If there's anything that leaves that has momentum, and the only place it got the momentum is from your original object, so you can't transfer the momentum 100% and then claim there were any losses to the environment. So this is back to the physics girl video that's so overtly wrong. It's such an overtly silly statement to say I transferred the momentum, 100% of the momentum went from this object to this object, 100% of the force went from this object to this object, yet half the energy leaked into the environment somewhere. Yet there was a whole bunch of little pieces that flew off, and there were all kinds of atoms moved and all kinds of stuff, vibrations and this and that. You can't do any of that nonsense. There's no energy. There's no place to get the energy from. So it's just more evidence that their formula is nonsense.
Words, any collision that happens between any number of objects, let's call it a system, the momentum of the whole system is always conserved. In other words...
Right. And so that's an absolute statement. Energy is conserved. You can't destroy energy. You can't destroy movement. You can only transfer it. You can only transfer the movement of an electron into an atom's movement, and then you can transfer that atom's movement back into a smaller force's movement. You can only transfer momentum. You can only transfer energy. That's all you can do to it. And their kinetic energy formula pretends somehow that isn't true. Like I said, it won't even say it overtly, though. It'll say somehow energy is always conserved. They're just making up extra momentum. They're saying I can 100% transfer the momentum, and yet there was a whole bunch of extra momentum that happened into the environment. That's impossible. That's a paradox. Can't be true. There's no physics to explain it. It's a holy ghost.
The initial momentum before the collision always, without exception, equals the final momentum. And so let's say we have two objects that are colliding. If we multiply the mass times the velocity of the first object, and we add that to the mass times the velocity of the second object, that's the total momentum of the system before the collision equals the mass times the velocity of the first object after the collision, plus the mass times the velocity of the second object.
So that doesn't really mean anything, right? Because we know that the losses are environmental, that they can be in terms of sound, okay, or they could be heat. They can be transmissions into the ground. They can be all kinds of other vibrations that have nothing to do with you maintaining two objects in the same condition, where you didn't lose any pieces. You didn't make any ions. You didn't shoot any electrons off. I mean, you didn't make any photons. You didn't do anything. So again, it's just kind of false to say, I'm going to show conservation. Now, if the objects themselves can't do any of those things, if the objects can't break, they can't emit electrons, they can't get hot, they can't do all these things, then you have no excuse and no way to get the losses into the environment. I mean, this is just too obvious.
Object after the collision. So this is I stands for initial, before, F stands for final, after. Now remember that direction is important because, after all, momentum is a vector quantity.
So again, it's just as much a scalar, it's just as much a everything. It's an amount. of something. It's an amount of force. It's an amount of energy.
So when something is moving to the right, we consider that positive direction.
Right, and that's so arbitrary, right? So you know that's just absolute nonsense. It's moving to the right, it's positive. It's moving to the left, it's negative. That's just absolute nonsense. We know there have to be opposing. You can't have a collision if the two things don't have opposing momentums. That is, momentums with an opposite direction vector. Some portion of their motion has to be opposite. Some portion has to be facing each other. So we already know that simple rule. And calling one side positive and one side negative is completely arbitrary. So we know it's not, they don't have positive and negative momentum. Something doesn't have unmomentum. There's no such thing as a negative momentum. It's just as positive as energy is. You're moving in a direction in the three-dimensional space. You're traveling in a positive, always in a positive direction. And they're just arbitrarily assigning a sign to one side or the other side. And they're not going to do the same thing when they talk about kinetic energy. Somehow kinetic energy doesn't have a sign. Of course it has a sign. If two trains are heading towards each other, the energy vector of one train is completely opposed to the energy vector of the other train. So one of them has to be made negative. One of them, you can't analyze the collision unless you have to make one of them negative, or else you think the end product is going faster than both of them.
When something is moving to the left, we consider that negative direction. So when you work out this equation, I'll show you some examples, simple examples later, we have to take into account the sign for the direction.
Duh.
Direction is important. So this hopefully will give you a good concept of what momentum actually is and why momentum is important. In the next few videos, we'll show you some more details to get more comprehension of the concept of momentum.
So again, they don't have a concept of momentum because they're going to completely destroy it with their concept of kinetic energy. They're going to completely lie and say momentum doesn't mean anything because the real energy is this magical extra energy you get by going further. This is so bad. So here's the one the guy actually linked to. Oh no,
We now have intel inside the Westview anomaly.
that's not the right one. That could be the wrong one. Oh, that's mechanics momentum. Okay. So that's not what I want. I want... Oh, how could he have all these different frickin' titles on these damn videos? So this is the one. Okay. So it's mechanics momentum, 2 of 9. Well, that other one said it was 2 of 9. Well, anyway, this is the one I want.
Welcome to Electron. One really good way to get a better understanding of what momentum is to compare it to kinetic energy, because quite often we get the two quantities confused, or at least the two concepts confused.
Okay, so let's just understand. There's no confusion. There was a huge controversy, not a little one, a pretty big one. Physicists were calling each other names. Okay, I mean, Voltaire was clearly saying this is, hooliganism. This is reverting back to religious nonsense. The invention of this babble. It was clearly sides. This is clearly contentious. This isn't just some superfluous friendly add-on. This is a replacement. This is an attack. It was invented by the person who, again, Newton's worst enemy in life. So just understand the context and why this was invented. This was invented by people who had been outdone, okay, by that guy. He jumped higher. He ran further. He ran faster. Okay, Descartes the same way. Somebody who did too much. He was too famous, too great, too superhuman. And they wanted to tear that down. These were just petty people looking for their own fame. And they thought they could make it by tearing down the great icons. So they tried to say Descartes was an idiot, or they tried to say Newton was an idiot. That's all they were doing. That's where this was all invented. So don't be playing this game that this is some kind of good science. This is the worst kind of possible atmosphere for science to take place, is when two sides have completely opposing views of the world. One side, the relativists, the mushiest, the etherists, okay, trying to defeat the particleists, the universe is a clock, the universe is a mechanical system. I mean, he calls this physics mechanics. This is physics by people who didn't believe in mechanics.
There's three main differences between momentum and kinetic energy.
The one difference is one's a religion and one's science. Okay, one difference is one has a ton of evidence defending it, one has no evidence that's reasonable. And 3, one is by petty weasels, and the other one is by good scientists.
First of all, momentum is a linear function of velocity. In other words, you double the velocity, you double the momentum. You triple the velocity, you triple the momentum. So you can
No, more simply, mass and velocity are equally important to the process. The bucket is just as important as the stuff you pour in the bucket. The size of the bucket tells you how much stuff the bucket can hold, okay? And the stuff you pour in is vital to the bucket meaning anything. The bucket can't mean anything if you don't put anything in the bucket. The two things are integral to the bucket having any meaning. The bucket only has meaning when there's fluid in the bucket.
see that if you draw a graph where we have momentum versus velocity here, that you have a straight line, and that the slope of that line equals the mass of the object.
Right, nice rational thing. It terminates. It doesn't go forever and ever. Okay, it crashes against the line of the speed of light. Okay, it's a real thing. It's rational. Kinetic energy, completely irrational. I can go infinitely up my little silly line.
P equals m times v looks a whole lot like y equals mx plus b. In this case, we don't have a y-intercept or a p-intercept because if the velocity is 0, you don't have any linear momentum.
So again, this comes back to even Einsteinian kind of arguments, right? There's two kinds of arguments you can have about when you're pushing something. So when you're pushing something and making it go faster and faster and faster, is the object getting heavier, okay, and it's harder to push, or is it getting lighter in the sense that most of it's going really fast and it's hard for me to push it any faster because I can't find slow bits to push on. So in a sense, as I'm making it go faster and faster, I can't find a slow bit to hit. I can't find a piece of it. It's getting invisible as I make it go faster and faster and more my own speed. I can't see it anymore. I can't find a piece of it that's going slower than my speed. So therefore there's nothing to push. Or do you believe that as I'm pushing it, somehow it's getting heavier and heavier and heavier, and each little atom is getting heavier and heavier and heavier? No, it's not getting heavier.
This goes away, you can see that the two equations are extremely similar, and the mass is the slope of that graph. Kinetic energy, on the other hand, is a...
So let's understand, the mass is essentially can be just converted into the weight. Your velocity and your mass is your weight. If you have no velocity, you don't weigh anything. If you're not moving, you can't push the scale. Okay, so it's just a measure of your weight, a quantity.
Quadratic function of v. The kinetic energy is 1/2 mv squared.
So again, it was originally mv squared. So for 70 some years, they didn't even know they needed to put a half in front of it. So the equation was so outrageously incorrect. It was twice as outrageously stupid. So where I gave you the comparison between the bullet and the bowling ball, both moved by exactly the same charge. So I explode a little bit of gunpowder, I move a bullet, and I move a bowling ball. Okay, same charge. The original formula was so far, so and I showed you how their formula right now for kinetic energy says the bullet has 457 units of energy and the bowling ball only has 7. Well, without the half, okay, it means that it's 800 and whatever the hell it is, okay, to 14. It's an insane ratio. You do understand that, right? It's an insane ratio.
Which looks a whole lot like y equals 1/2 kx squared, k being some constant. In this case, a constant is, again, the mass of the object. But notice that as velocity increases, kinetic energy increases much faster. You double the velocity, you quadruple the kinetic energy. You triple the velocity, you have 9 times the kinetic energy.
Right, so he just keeps saying things like that, right? So I can just make energy by putting lighter things and making them go faster. I am making more energy in the universe. So I take the same explosive charge and I just keep putting lighter and lighter and lighter things on the charge, and my energy, the amount of energy I'm making in the universe, increases exponentially. I mean, again, how is this not Holy Ghost science? How is this just not complete nonsense? How does that not break every concept of reason and rationality there could be? How can the same explosion make more energy just by making the pieces it throws slighter. Make more little pieces and somehow I've made more energy. Make big, heavy pieces, I make less energy. It makes no sense.
That's not the case with momentum. The second main difference between the two, that in a collision, momentum is always conserved, just like we saw.
So again, in a collision, it's always conserved. The idea is no, it's not just transferred, okay? So in a collision, you can transfer it really efficiently or you can transfer it very inefficiently. And if it's inefficient, the conservation is going to be a lot harder to catch, okay? Because it's going to be in a lot of little pieces.
On the first video, whatever the momentum of the system was, the momentum of each individual piece of objects colliding with one another, when you add up all the momentum after the collision, you get the exact same momentum as you did when you add up all the momentum of the...
Right, so that's just logical, right? Purely logical, that you always have to account for the energy. So if we call momentum energy, you always have to account for the energy. And now he's going to say, but our new wonderful energy formula says you don't have to do any of that accounting crap.
Objects before the collision. With kinetic energy, that's not at all the case. In other words, in a collision, kinetic energy is never conserved. And I say, well, wait a minute, I've had problems in my textbook where kinetic energy is conserved, and that's only in a textbook. In the real world, kinetic energy is never conserved. Although...
So now he's using the word conserved to mean 100% transferred. So we know the idealistic textbook examples are just saying, look, I have a 1 ton, 10 mile an hour train. I'm going to connect it to another piece of 1 ton weight, and now it's going to leave at 5 miles an hour. That's a perfect transfer. Now, technically, they should say it's going to leave at 4.99 miles an hour because I have a really efficient coupler and it's going to stick really easily and there's not going to be any big sounds and there's not going to be sparks and there's not going to be all that kind of crap. So I'm not going to lose much energy at all in the transfer. So now he's using the word conserved to describe the transfer. There's no 100% transfers, okay? But that doesn't mean you have an excuse now to say half the energy was lost to heat, sound, and other kinds of crap. So again, look at the way they're using the word conserved. He's saying in a collision, kinetic energy is never conserved, except in the perfect circumstance where you transferred it 100%. I mean, it's, see, so they're just using the same word. Transfer and conserved are being confused with each other, and they really shouldn't be.
To get more practice in physics and in a textbook, sometimes we say that the collision was 100% elastic or simply was elastic.
Right. So when they say elastic, they're just saying, talking about the quality of the transfer. Elastic and inelastic is the quality of the transfer. It has nothing to do with whether you're going to lose energy to the environment or not. It has to do with whether you're going to transfer the energy efficiently.
But in the real world, that doesn't occur. Now, at the quantum mechanical level, with atoms and electrons and protons, yes, that can occur.
Right, because there's no friction, no atmosphere, and no bad couplers or any of that kind of crap. So there's no friction in the smallest universe. Friction is just the fact that we live in a chemistry. We live in force. We live in an environment full of places where we can't interact with it. Two hands can't interact with each other with the atmosphere getting in the way.
Everyday life, when we do problems in a textbook, unless it says it's 100% elastic, which of course is just a fictitious thing, just like there's no wind resistance in our problems in physics either, we can say that in a collision, kinetic energy is never conserved. You always will lose some energy when things collide.
So again, you're not really losing the energy. You can't lose it. It can only go into the environment, just like momentum. And just like momentum, you can't conserve the momentum, that is, transfer the momentum 100%, or 98%, or 99%, and then say, but there was 50% loss to the environment. You can't have a 2% loss in the transfer and then claim that 2% is 50% of the energy. That's ludicrous. The 2% can only be 2%. It can't be 50%.
Wide. And finally, notice that momentum is a vector quantity, just like we showed.
So again, more made-up jargon, okay? Both of them have mass and velocity in the equation. Nobody could think putting a half in front of it could mean anything, okay? Oh, now it's a vector quantity because there's a half in front of it. And likewise with the squared. That can't mean anything either. You can't change what it is, okay? It's meters and seconds. You don't change meters and seconds by putting a square on. You really don't. And you don't change kilograms by putting a square on it. That's just like putting a half in front of it. It can't mean anything. So the quantities are still there, okay? And all you're just saying is how much of the stuff do you have. But the ability to transfer it into euros, like it's still in dollars. You didn't convert it into banana tree, okay? You didn't convert it into something like, you know, 1/2 of a Cheez-It. You didn't convert it into something as non-convertible. You're just saying, no, you can convert it right into euros if you want to. It's in dollars. You can convert it into euros.
In the first video, so when an object is moving to the right, we can say that it has positive momentum. When an object is moving to the left, we can say that it has negative momentum.
Okay, and you have to do exactly the same thing when an object is moving to the right or left, and you call it kinetic energy. If the kinetic energy is moving this way and one kinetic energy is moving that way, you have to give one of them a minus sign or you can't do the math. So this is just, again, isn't this just a rationalization? I mean, how can the double standard be more obvious? Of course you have to put a minus sign on them, but momentum never is negative. There's no such thing as negative momentum. There's no such thing as negative kinetic energy. This is just baby bullshit. This is just such a weaselly contrivance. Like somehow this is a real difference. We arbitrarily decide to call the left hand negative, but we're not going to arbitrarily do the same thing to the energy equation, even though you have to actually do the equation. You're going to have to put the minus sign on one of the pieces of energy. Oh, it's just so pathetically, obviously snookery.
And we do have to keep those directions in mind when we start working out problems involving momentum.
Shenanigans, right?
On the other hand, kinetic energy is a scalar quantity. And
so again, it doesn't mean anything. They're both scalar quantities. Just convert the Newton meter seconds into joules. Done. Okay? Just convert it into watts. Doesn't matter. Momentum can be converted into watts. Perfectly doable.
Since kinetic energy is equal to 1/2 mv squared, since the velocity is squared, the squared velocity can never be negative because it's squared, and of course the mass can never be negative.
So obviously, but you couldn't do the formula though unless you did make one of them opposite the other. You have to subtract their energies in opposite directions. So it's just silly. It's absolutely silly nonsense.
Words, kinetic energy can never be negative. That's not the case with momentum because since...
So obviously just nonsense. It's just nonsense, right? I mean, it's nonsense. Of course you have to do the product. You know, you have to figure out what happens when I combine the two things. And there's no way you get to add up both their energies and say, okay, it's now 1,473,000 joules. No, you don't get to do that.
It's a vector quantity, it can be moving in a positive or negative direction, and therefore it can have positive or negative momentum. Kinetic energy can only be positive, and it's a scalar quantity.
So again, just words, just absolute babble, can't mean anything to anybody who's doing the rational equation. The energies will cancel each other. It's just a fact. So they're going to cancel each other just like the momentum does. And they're going to add just like the momentum does.
Those are the three main differences between momentum and kinetic energy, and hopefully that will help you understand what momentum is.
So obviously that was not at all helpful. So this jargon that somehow I have mass and velocity over here, and I have mass and velocity over here, and because I put a half here, if I put the the square root of W in front of it, does it somehow make now this is some kind of new thing that I can't figure out how much it is anymore because I put some other number in front of it? Of course I can still figure out what it is. It's just nonsense. Alright, it's just them telling a story, okay? And here they're telling you the phantom story. The holy phantom. Anyway. So I don't know whether part 3 is worth it because, like I said, we really want to stick to this kinetic energy thing. So maybe I will look for kinetic energy videos by Van Biezen. But again, he doesn't get to any theory. He just does his mathematics. So in most of his videos, forget it. He's not going to explain why it is. He's just going to say this is what we say. But what will be clear is kinetic energy always gets the wrong answer, frankly. I mean, the only time it gets the right answer is when the two objects have exactly the same mass. Then it can get the right answer. But as soon as you change the masses, it gets wrong answers all over the place. I mean wrong in that they lose proportionality. That's when this curve starts going all wacky on you. See, there's one, the straight line intersects this curve at a certain spot, and at that spot they get the same answer. But everywhere else they get the wrong answer. They're not the same answers. So yes, you have one little spot, on the curve where they get the same answer. But that's only when you have certain proportions of mass to velocity that you can make the two formulas compatible. But otherwise, they're always incompatible, always giving you a different answer. And again, if you had to navigate a spaceship based on one of these formulas, based on one of these rules being the rules of energy, which one is the rule of energy? This nice straight line, proportional line, or this little wacky curve line? And if you had to invest in one of those for your life, I'm saying, yeah, momentum is that's the go-to player here. That's the guy that's going to get the touchdown. This kinetic energy shit, no, it's going to be running the wrong way. It's going to score a field goal in soccer, right? Yeah, it's not going to do the right thing at all. Maybe you can do that. I don't know. Soccer is weird. But it really couldn't because there's no goalpost, right? So how could it get a field goal in soccer, right? You can't really do it. Anyway. Fuck. Sorry, I shouldn't. Shoot. God, you people are dense, thick. Just, you're being silly. Stop it. It's embarrassing for the human race. I mean, really, just imagine your conversation with the aliens. They show up with their everything worked. We got here. We do this nice straight line stuff. We're men, alien men. And what are you girly physicists with your little, what is this pink pansy little bullshit? What is this pansy physics? What are you talking about? MV squared. What do you mean? Why? Why would you do that? That's just silly. Well, light things go further. And the aliens be like, duh. So you think it has more energy because it went further? Boy, you're really dumb. They just enslave us instantly. Just say, you're really too stupid, right? You're not like grown up thinking on machines. You're rabbits. I mean, we'll go have you eat our grass at home or something. Twitch your nose because you can't do any of this thinking thing. Logic. You really don't know what logic is, right? This holy ghost formula. You really don't understand how silly this whole thing is. That this is just never useful. This will always work. Momentum will always work. They're never going to show me any experiment ever done where momentum doesn't get the right answer. And yet somehow we need this other jerky formula that almost never gets the right answer. Now, if it isn't religion, what is it? We know where it was invented. We know how bad the physics is. We know how bad the experiments are. Again, they think I shoot something into gravity. Two things. A light thing and a heavy thing. And I use exactly the same energy to kick them. I kick them with my foot or whatever. They think because the light thing went further, it has more energy. That's how they think. Yeah, okay. All right, well, I can only reason with you, but there's no point in reasoning with you because you're not reasonable. That's a big problem, frankly. When you can't do logic and reason, when you can't just point out all the tons of facts. Like I say, when I put all the facts on one side and they're all there and you don't answer any of them. You don't explain any. I mean, I can keep saying they never did the, they never did the, what's the name of the guy with the frickin' solar eclipse experiment? Yeah, I shouldn't really be able to even forget his name. It's so ingrained in me. But anyway, the Eddington experiment. Never did it from space. 400 times better resolution. You people think that's logical. They've had all this time. I mean, they're doing minutia now, right? They're spending millions of dollars to do the silliest thing. Yeah, but let's send another probe to Mars, right, to see how red the red colors are. Because, our other camera it doesn't get the full redness. So we need a better picture that has more redness in it. I mean, there's nothing to see there. They've already taken all the pictures you need. They're so microscopic. I mean, they're looking at the little grains of sand and dust. Right? but they don't do the Eddington experiment, one of the most important experiments in the history of physics. It's never been successfully replicated, ever, and they don't do it. And it would cost like $75. They don't do it. So are they genuine scientists? Are they really looking for the truth when they ignore something so obvious? I mean, a foundational experiment never duplicated. Ooh, that's one of the foundational things. We're supposed to always duplicate experiments. Ooh, we shouldn't have let that one slide, huh? So it does make a joke out of physics. It does provide evidence that you can't believe anything these bandwagon riders are saying. They're just singing the banjo song. We're singing the banjo song because they taught us the banjo song. It might seem like we are creative and we know how to do stuff, but no, I only know how to sing, and all I know the lyrics to is the banjo song. We just sing the same old song. We sing it over and over because our mother and papa told us, and our professors told us this is the song we sing. We don't sing any other song because we're not creative, we're not thinkers, we don't give a shit about anything. We just ride our fucking goddamn, gravy train of bullshit. This has been a Draft Science video presentation.